Welcome. We are Team Cerberus from Seattle Pacific University, and this is our final presentation for the Cornell Cup. I am Chris Howard. With me is Nathan Cho, Luis Pieri, Adam Marsh, and Lucas Oliveira. So the problem that we saw in the world is that fires cause a lot of damage, both over $11 billion and 3,000 civilian deaths annually, just in the US alone. And the main reason that we looked at that is actual firefighters just are too slow to get to the fires in time. They can take, even in an urban area, up to 9 minutes, and in that time, fires grow exponentially. We've designed CERBERUS to provide a minute zero response time solution to this problem. In this presentation, we're going to cover a couple things. Challenge definition, what we're trying to solve. Solution, technical ingenuity, how we executed the project, the next steps that we do if we were continuing this project, and leave a little time for Q&A.
So the challenge for this project was basically to design a system that can improve upon and reduce the cost of existing methods of fighting fire, as well as minimize the damage caused by fires. And we feel that a good solution to the problem will be nearly instantaneous, autonomous, maneuverable. It will effectively and efficiently find and fight fires, and also be affordable. So our solution to the problem is CERBERUS. It's an on-site firefighting robot that basically sits and waits for a signal from a fire alarm control panel. And once it receives the zone information of where the fire was detected, it'll use a camera to follow a line to the zone. And in the meantime, it'll use its sensors, distance sensors, to avoid obstacles and prevent collisions. And then once it reaches the target destination, it will be able to suppress the fire. We feel that this system complements the existing fire sprinklers you'll find in most buildings, and it aids firefighters before they're able to arrive on scene.
So when we started this project, we were planning using the Arduino Mega 2560 as our microcontroller. When we were using that, we could implement the line following algorithm, work at roughly 75% of our speed. It's more or less 9 miles an hour. We implemented our fire tracking algorithm, our extinguishing system, and we started partially integrating everything. And then we made to the finals of the Cornell Cup, and we had to change for Intel processor to control our robot, and then we chose the Intel Edison as our controller.
So during the transition to the Intel Edison, we encountered many issues that set us back for a few weeks. We had issues with the cameras, the communication between the cameras and the Intel Edison. We had issues with our ultrasonic sensors, and we also had issues with the PWM signals that control our motors. So right now we have basically the fire extinguishing system operational, and also we are able to track a source of fire with the camera on the nozzle.
So our main goals for the programming part were make the line following algorithm working at roughly 85%, is more or less 10.5 miles an hour. Implement the obstacle avoidance, implement the room searching algorithm. It's the fire tracking with the obstacle avoidance algorithm, more or less, and put everything together in a final product and very useful. Another thing is our line following algorithm. I did a quick research on the internet. I couldn't find any related algorithm using the Pixie to follow multiple line colors and at the speed that we are running our line following algorithm.
Something else we're quite proud of is actually the kick plates. They're not currently on because of the technical issues we described earlier, but when we were designing the product, we recognized that firefighters and fleeing civilians would have to be able to temporarily or permanently disable the robot in fairly frequent use. And so we needed a simple solution to be able to do that, and so we developed the kick plates to where all you have to do to disable the robot is just try and punt it. After that reasonably easy motion, you can then either wait for it to come back online after a couple seconds, or permanently disable it through the use of the kill switch.
Great. Just a little bit of a project execution overview. Some issues that we did come across were just the angular vertical displacement of the nozzle. The nozzle is effectively rubber, and so when there is a force being pushed onto it, it just moves up horizontally and doesn't have an angular displacement. To solve that problem, we made a metal brace for it, so now the nozzle is more rigid and it gives us a nice angle up and down. Some other issues that we had were just the ability to power 2 different cameras at the same time. Our original design only accounted for one, and so when we integrated the second camera, we had some issues having both of them work at the same time. We also had issues within our program, just integrating all the different systems together in the respective programs into one CERBERUS, obviously, we're having issues with. But that kind of dips into the accomplishments. All the individual subsystems that are comprised in CERBERUS work fine with their own respective programs. All of our mechanical systems are working perfectly and are designed quite nicely, and our fabrication is looking awesome.
So to get here, we obviously needed funding and design. For the funding, we originally started out with a design plan for the 1500 that Cornell graciously provides its teams that make it to the finals. But through some trial and error, we discovered that a budget near $2,000 was more appropriate for our challenge. And so through the university, through scholarships and grants, we were able to successfully get that money, and we're proud to say that we're basically fully funded. For the design, we went through 8 iterations, which we'll cover in just a second, and also including a PCB swap and the addition of a bunch of components over the base. So version 1 and version 2. Version 1 was the first initial, basically it's eye candy. It isn't actually representative of any good actual technical designs, but it was to get the team excited to be able to work on a cool looking project. Version 2 was actually the first start designing of the actual robot. You can see that the top plate is molded to be able to fit the contours of the detection cones of the ultrasonic sensors, and still using a 3-wheeled omnidirectional drive system that the version 1 had. It was kind of our exception, and it has white ghost boxes for where the electronics would go, because we didn't at that point know what electronics we were going to use, but we knew that we were going to use some, and we wanted to set aside space for them. So version 3 is probably the most drastic change in any of the different versions. This is when we decided to go from a 3-wheel omnidirection into a 2-driven wheel coaxial system. There's a lot of good detail expanding on this in the design report. So for now, I'm just going to gloss over it. And at this point, we also selected most of our electronics, the motor controllers, the Arduino, things of that nature. And we also did visit the fire department, where it shows the color of the light, the kick plates, and other things that helped really solidify this into this really being the first robot that we had designed. We also added all the auxiliary components like the light, the buzzer, the breakers, things of that nature. This was the first robot. This is the sensor layout. The blue cones and lines are the ultrasonic distance sensors and IR distance sensors respectively, and the pink cones are the IR flame sensors. And so this is basically the eyes of the robot that we still more or less use to this in version 8. Version 4, the main change was the extinguishing system and integration of the PCB.
Yeah, so this is our first iteration of the extinguishing system. It's very rudimentary. The IR flame sensor is actually connected by a piece of U-channel that is tied down onto the nozzle with a pipe clamp. And so it's very, very simple. Functionally wise, it was designed to function to our needs, but for the looks of it, it's not anything special.
Yeah, the first version of the PCB was simple as well. It served mainly as a power distribution board. So we had an input for our 14.8 battery. We had a couple of regulators regulating the 14.8 to 5 volts and 12 volts to power all of our sensors, the lights, and the buzzer.
Version 5, the main change that we discovered that the ultrasonic distance sensors don't actually have a circular cross-section for their detection cone. They actually have a very elliptical cross-section. And thus, when we were trying to drive the robot, it was actually seeing its frame as a wall in front of it, and so it was completely throwing us for a loop until we discovered this issue. And so the correction to that was, instead of mounting them vertically, we mounted them horizontally so that the detection code no longer intersected the frame. Version 6, the main change is a little bit the extinguisher, but mostly the PCB.
The new version of the PCB was roughly 65% bigger than the first one. That increase in space allowed us to have the PCB as a chute for the Arduino breakout board for Intel Edison. So now with the new PCB, we have data signals from sensors, we have power to all the sensors, basically everything we need. And we reduced drastically the amount of wire inside the robot.
And the extinguishing system, just the nozzle mounts are just 3D printed now instead of having different metal components combined together.
Version 7, we needed a little bit more actuation in the Pixie, or for a line following camera. And so for this version, we mainly just defined and catted out the Pixie in greater accuracy and was able to 3D print the mount that it sits on. Version 8 is the version we're currently on, and mostly it's an extinguishing update.
Yes, so like I said before, the nozzle is now more rigid now because we implemented the metal brace onto it. We also got to a point where we're getting rid of the IR thermal sensor and replacing it with a second Pixie camera. And so we had to do a redesign on the front end of the mount so that it'll be able to fit the Pixie camera on top of it. And we also redesigned the whole support system for the extinguisher. Using this design with riveted parts, it is more functionally reliable and more rigid. And yeah.
So there's a couple different things that we would like to do going in the future if we did actually continue with this project. Big ones are stair climbing and actually opening doors. They're kind of elephants in the room in that with a building such as like an office building, it really wouldn't. The Cerberus as it stands right now really wouldn't be able to do much because of the doors in the way and that there's multiple floors. In a grocery store or a warehouse, however, we think this would actually be a reasonably appropriate solution to firefighting. Also, some refinements that we could make is we could definitely streamline the process because of additional components we put in just in case we needed, but we turned out that we didn't actually need them, so we'd be able to remove those in a second version. Additionally, there's a lot of computational stuff that we could probably improve with navigation algorithms and fire sensing, things of that nature that we really just need the time to be able to refine the process. And with that, our presentation is over. We look forward to seeing you in the competition proper, and have a nice day or evening or night.